The question we are asked to solve today states, determine how many of these molecules are polar. So in order to be able to solve a question like this, there are three major things we must do. The first thing we must do is draw the Lewis structure. After we have the correct Lewis structure drawn for each of the molecules, the next thing we must do is identify the bond dipoles by looking at the electronegativity values of each element. Those electronegativity values can be found by looking at the chart or by just looking at the periodic table to determine which one has a higher electronegativity. After we find the bond dipoles, the next thing we must do is look at these bond dipoles and the molecular geometry in order to determine the net molecular dipole. Once you've determined the molecular geometry and the net molecular dipole, you can then determine how each one of these molecules are polar or nonpolar. The first compound we are going to do is SO3. So the first thing we must do to solve this equation is draw the Lewis structure. So whenever you're drawing a Lewis structure, the first thing you have to do is figure out the total number of valence electrons. So when you look at the periodic table, S has 6 valence electrons, and oxygen has 6, but there's 3 oxygen, so we do 3 times 6. You add that up and you get 24 total valence electrons. Now that we have the valence electrons, you put the least electronegative element in the middle. So it's going to be an S in the middle with a single bond connecting to 3 different O's. So now that we have the single bonds, we want to make an octet for the outside atoms first. So we already have 2, 4, 6 electrons used. So it's going to be 8, 10, 12, 14, 16, 18, 20, 22, 24. Alright, so we have all of the electrons correctly used with the octet on the outside elements. However, the S in the middle, the center atom, does not have a full octet, so that's going to require us to make a double bond with one of the O's. For this equation, this molecule is going to have resonance, so it does not matter which O you draw the double bond on, just as long as you have it. So when we make the double bond, the Lewis structure was going to look like this. Still single bond with a double bond on one of the O's, and then you're still going to make sure all of your elements have an octet. Alright, so now we're going to check the valence electron again to make sure we still have 24 and each of the elements have a full octet. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So this element, each element has the correct number of valence electrons. They all have 8, so S is, now that the double bond is, S follows the octet rule as well as all of the other outside elements. So this would be the correct Lewis structure for SO3. Now that we have the correct Lewis structure of SO3, we are able to figure out the bond dipole. So when you figure out the bond dipoles, you look at which element is the most electronegative. So in this step, what we do is we figure out the partial negatives and partial positives. O is more electronegative than S, so your O's in this molecule are going to be partially negative, while the center atom of S is going to have a partial positive charge. We use these charges to determine the bond dipoles. So the bond dipoles are going to go from the center atom, stretching out, pointing towards each of the O's. So now that you have the bond dipoles, the last thing we must do is determine the net molecular dipole and the molecular geometry. So this element has 3 domains, and it has all of the domains are the same. There's no non-bonding pairs, so this molecular geometry is going to be trigonal planar, and this is what the trigonal planar molecule looks like. All the bond dipoles are going to be pointing out towards the O's, and there's no net molecular dipole because all of the bond dipoles are the same, so they're going to cancel. Because all of the bonds cancel and there's no net dipole, we can then look and make sure that all domains are the same. For this molecule, all the domains are the same, so therefore this molecule is going to be nonpolar. The next molecule we use is going to be OF2. This is the correct Lewis structure for OF2. It has 20 valence electrons, and here we have it shared to where each one of the elements has a full octet. Now that we have the Lewis structure, we must find the bond dipoles as well as the partial negative and partial positive charges. F is the most electronegative atom on the whole entire periodic table, so F will have your partial negative charges while your O in the middle has your partial positive. You look at these charges and that allows you to find the bond dipole, which is going to start with the O and point out towards each F. Now, after we have the bond dipoles and the partial negative, partial positive charges, we can determine how many domains there are and therefore determine the molecular geometry. So this equation is going to have 4 domains, 1, 2, 3, 4. 2 of them are going to be equal, and then there's 2 non-bonding domains. So when there's 4 domains and 2 non-bonding, that gives you a molecular geometry of bent, which is going to look like this. So when we look at this shape, the bond dipoles are pointing down towards the F's, and all of the domains are not going to be the same, so therefore there will be a net dipole because the bond dipoles will not cancel. So the bond dipoles are going to be pointing towards the F's, which means that the net dipole will be pointing down for the molecule. Now that we have a net dipole, we can also check. We said that all 4 of the domains are not the same, so that's going to allow us to determine that the molecule is in fact polar. It's going to have a net dipole pointing down because the center atom, the bond dipoles going from the center atom to the F will not cancel. So it'll have a net dipole pointing down and the molecule will be polar. The next molecule we're going to do is BeCl2. So this is the correct Lewis structure for BeCl2. We have 16 total valence electrons, but what's weird about this one is that Be does not follow the octet rule. But if we look back at our notes, we can see that Be as well as B are 2 elements that are allowed to accept and break the octet rule. So now that we have the correct Lewis structure, we can figure out the bond dipoles. Cl is more electronegative than Be, so your Cl's in this molecule are going to have your partial negative charge, while your Be has your partial positive. When your Be has your partial positive, that means that the bond dipoles are going to start from the center atom of Be and point out towards the Cl's. So after we have the bond dipoles, we next must figure out the molecular geometry. So there's 2 domains for this, and there's no non-bonding, so that means that the molecular geometry is going to be linear, which means that the molecule looks the exact same as it would on this note card. So your bond dipoles are going to go from your Be to your Cl, and because the bond dipoles are going from the center atom to the Cl, they're the same size and there's no non-bonding. That means that those bond dipoles are going to cancel and there will be no net molecular dipole. Now that we've determined there's no net molecular dipole and both of the domains are the same, that allows us to say that this molecule will be nonpolar. The next molecule we do is CCl4. So CCl4, this is the correct Lewis structure because all of the elements follow the octet rule and the C has 4 bonds, so the center atom follows the octet rule as well. After we have the Lewis structure, we can then determine partial negative and partial positive. Cl has a higher electronegativity than the center atom of C, so your Cl's will all have your partial negative, while your C in the middle has a partial positive. That means that your bond dipoles are going to stretch from the center atom pointing out towards the Cl. Once we've determined that, we can then again find the molecular geometry. This molecule has 4 domains, all bonding. There's no non-bonding, so the geometry will look like this for a tetrahedral. When all of the bond dipoles stretch from the center atom of C to the Cl's, when they're all the same size with no non-bonding pairs, that means that the bond dipoles will cancel and therefore there will be no net molecular dipole. Once we've determined that there's no net molecular dipole, we can then see that all of the domains are the same and therefore this molecule is also nonpolar. The last molecule we do is O3, also known as ozone. Now this molecule is a little bit different because once we have the Lewis structure, we can see that it's the same element going for all 3 of the elements that are in this. And that allows us to determine that this molecule ozone is going to be a little bit different. So there will be no bond dipoles because whenever there's 3 of the same element, they all have the same electronegativity. So you can't determine which one would have a partial negative or a partial positive charge, so therefore it will not have any bond dipoles. So now there's going to be no partial negative or no partial positive and no bond dipoles. But we can still determine whether or not this molecule is polar or nonpolar by looking at the molecular geometry. So this molecule has 3 domains with 1 non-bonding, which means that the molecular geometry will be bent, so it will look like this. When you look at this, you can see that even though there will be no net dipole or no bond dipoles, we can see that all 3 of the domains are not the same. And as we check back in our notes, when all 3 of the domains are not the same, the molecule will be polar. So now that we have all that figured out, we can go back. We said SO3 was nonpolar. OF2 is polar because all of the domains are not the same. BeCl is nonpolar because all of the domains are the same. CCl4 is nonpolar. All of the domains are the same. And then our last one, O3, which is ozone, is going to be polar because the domains are all not the same. So when we look back at this question, it says determine how many of these molecules are polar. So for the answer for this question would be OF2 is polar, as well as ozone or O3. A common mistake used whenever you're trying to figure out this problem, many students do not draw the correct Lewis structure for each of the molecules. When you do not draw the correct Lewis structure, that inhibits you from being able to follow the next 3 steps correctly and be able to determine the molecular geometry, which will help you determine whether it's polar or nonpolar. So a major step in this is drawing the Lewis structure, and if you do not do that right, then it would be impossible to get the rest of the question right.